Welcome back, everyone. From our last lesson, we saw what a function is. And in today's lesson, we are going to be looking at limits and derivatives of a function. So today's lesson focuses on finding the limit or understanding the relationship between limit and differentiation. Okay, so let's say we have a function f of x. How can you describe or monitor the rate of change of the function f of x? We can do this by computing the limit of that function as x tends to a certain value. Now, for example, let's say we have a function given by f of x equals x squared. Now, I want us to evaluate the limit of this function as x approaches 2, both from the right and from the left. And then we see how the function f of x behaves as x approaches 2. So what are we saying? If we have on the board, if we have a function, say f of x equals x squared. Now, how can we evaluate the limit of this function as x approaches 2? Mathematically, we write this as the limit of x squared as x approaches 2. And what will this give us? This will just give us 2 all that squared, which will be 4. Now, this is how we represent or write this the limit of a function mathematically. So we have a function f of x. We want to compute the limit as x approaches any point on the x-axis of that curve of that function. This is how we do it. We show it mathematically. Now, what is the significance of this? How does this describe the rate of change of the curve? Now, let's explain this using a graph. Now, so let's say we have a curve here, and this curve represents f of x equals x squared. Okay, now I want us to try approaching 2 from the left. Approaching 2 from the left means that we start from somewhere up and we are approaching 2 in the left direction. Is that okay? Okay, so let's say at some point, we can say at some point x equals 2.6. Let's say if x equals 2.6. If x equals 2.6, if we substitute 2.6 in x squared, we are going to have 6.7. So at x equals 2.6, f of x will be 6.7, and that is going to be somewhere above here. Okay, now as x approaches 2.3, we have f of x at to be 5.29, and that's 5.29 is also somewhere around here. Okay, now this is not a perfect curve because the scales ends just at 1, 2, 3 to 4, but we are having values of y that exceed that, and because of the understanding we have in graph, we know that those values can only fall in this path. Is that okay? Along the curve. Now, what if x approaches 2.1? If x approaches 2.1, we'll have our f of x to be 4.41, and that's going to be somewhere around here also. So we notice that as x approaches 2 from the left direction, f of x reduces to what? To 4. Now what if x is finally 2? At x equals finally 2, f of x is exactly 4. At x equals 2, f of x is exactly 4. f of x is exactly 4 at x equals 2. So this is how the curve behaves as we approach 2 from the left direction. Now let us approach 2 from the right direction and see what f of x, or see how f of x behaves. So if we're approaching 2 from the right direction, it means we are coming from this direction, okay? And let's say for f of x equals 1.5, if we compute f of 1.5, that will give us, f of x will be 2.25. So for x at 1.5, we'll have f of x being 2.25, and that is a point which is somewhere around here, because this is 2 and this should be 2.5, okay? And for x, let's say we are approaching x equals 1.8. If we compute f of 1.8, that should give us around 3.24, and that will be around here. And so what do we also notice? We are noticing that as we approach 2 from the right direction, f of x is also approaching 4. Now, when we finally get to 2, like we did, we will see that f of x is exactly 4. Now, what does this tell us? So, mathematically, we can write this as the limit as x approaches 2 from the right is equals to, of f of x, which is x squared, is equals to 4. We have seen this, from the graph, right? And also we can say, we have also seen from the graph that the limit as x approaches 2 from the right of f of x being x squared, this is also 4. Now, since the limit as x approaches 2 from the right is the same as the limit as x approaches 2 from the left, what does this tell us? It tells us that the limit of the function f of x equals x squared actually exists, and the limit is equal to 4. Now, what is the significance of this with the derivative? This concept of limits is very, very, very vital, especially in advanced physics concepts, in deriving and proving physics formulas, because it tells us the instantaneous rate of change of the curve. It tells us how the curve, the rate at which the curve, it tells us how the curve behaves as we approach a certain value. Is that okay? Now, since the limit of this particular function f of x equals x squared, as we approach 2 from the right, since the limit is 4 from the right of 2 and from the left of 2, this tells us that the derivative of this function, now let's write that on the board. This tells us that the derivative of d of dx of the function x squared at x equals to is equals to 4. Okay, so this is how the limit of a function, computing the limit of a function, actually describes the behavior of a curve. Thanks for watching. Now, if this helped you understand something, make sure you like, comment, and share with your friends so they can also benefit and learn something. See you in our next lesson. Bye.